Hi, everyone, and welcome back to part 2 of the LLM as the interface for tools, plugins, and APIs. And just in this 1 week that we have been away for, lots of things have happened in the AI world. So let's just take a look at some of the advancements that will deal directly with our topic today. So first up, we have an advancement to visual ChatGPT. Remember last week we were talking about like the prompt manager and then the API. Prompt manager tells GPT, do you need to use a tool? And then GPT will create the tool itself. So the workflow last week was like that. Let me just write something down. Okay, annotates. So the workflow last week was like that. Like GPT will ask, the prompt manager will ask in this fashion. Like they'll ask in the, you have the observation, you have an action input. Okay, maybe not observation, like thoughts, action input, explanation, or as an observation. So this is called the React format, and the GPT will like keep going step by step. Okay, you are at this step now. What tool should you use? The action is what tool should you use? Then after that, GPT will respond like, okay, I want to use maybe the image question answering tool. Then you go to the question answering tool, get the response, output as a text. The question answering tool has given you back this image. The image description is as such. So you will do this in an iterative manner. So that was what was done in the past. We did it in an iterative manner. So in this case, the past refers to like just 1 week ago, because that was the dominant approach in the past. All right. This week, this paper came out on 28 March. This does it in a different way. So instead of just doing it in an iterative format, what this paper is doing is that you are doing a meta plan, a grand plan first. So you can take a look over here. Like you have the user instruction here. This is the same as Visual ChatGPT. But instead of going through the action straight away, you have a solution outline, which outlines like step 1, do this. So the solution outlines like that. Step 1, do this. Step 2, do that. Step 3, do this. Yeah. So you already outline every step you need to take. So this is like a meta planner, and surprisingly, they managed to get a GPT model to actually give the list of steps to do the instruction. So this is something similar to SayCan. If you've seen the presentation on SayCan, where you give it like a goal, in this case, the user instruction, and then the model can then give you step 1, do this, go to the Coke bottle. Step 2, pick up Coke bottle. Step 3, bring to user. Step 4, pass the Coke bottle to user, something like that. So instead of doing the React approach where you do a thought, action, observation, what this TaskMatrix.AI is doing is it gives an outline of the solution. Thereafter, the solution would then be executed one step at a time. So this solution outline will be the context. All right. And then you will execute one by one. Go to step 1, go to step 2, go to step 3. Yeah, I'm not too sure whether this whatever you get from your action can actually inform back again the solution outline, because sometimes you might get something unexpected. Then you can refine your plan again. I'm not sure whether they did that, but I think that is also easily implementable by giving this part here back to the solution outline. So it's some form of hierarchy, which I will be talking about more in the later few slides. But then the main thing here is you have exactly this hierarchy. You have this solution outline. This is something that is not present before. All right. And another thing that is different in this task matrix, if you look over here, you have millions of APIs. All right. So this part, I don't think they have implemented fully yet. Okay. Because if you remember correctly, each API will need to give you like a description of the API, what it does, input format, some examples, which is optional. So this is like the plugin format. Like you need to say all this. Imagine you have 1 million plugins. You are not able to get all this done in just your 32,000 tokens. So what people normally do is that we have to do it iteratively, like over a few times. You ask the model for the first 10 plugins, then ask the model for the next 10 plugins, and so on. So what Microsoft, this is by a Microsoft paper actually, what Microsoft proposes is that you can train this using fine-tuning to basically let the model learn how to use the various API, and then you don't need to use the in-context prompting anymore because you fine-tune already, you already know which API to use. And there's also another part here that they try to do some form of learning. Okay, so the reinforcement learning part to learn the like fine-tuning is here, this RLHF. I think you can also do the supervised fine-tuning. RLHF not really needed. All right, so this part here, this feedback, I think this is quite cool because this is exactly what I was thinking as well, to let the model learn. In order to let the model learn, you need some form of learning signal. And this learning signal could happen in this big model itself, this model here, which is like ChatGPT, or it could happen in the APIs. And you know, if ChatGPT was to be a service, it would be quite difficult to fine-tune the ChatGPT because every time you fine-tune it, all right, you have a different model. Then you need to run a separate instance in the cloud. So the more cost-effective way of running it will be to edit these APIs directly. So you let the APIs learn by some feedback that the model have, like, okay, this use case 1, solve. Use case 2, not solve, something like that. Use case 1, solve. Like use case 2, not solve. So the API can learn what to improve on. So I find this part quite cool. And yeah, so this more or less what this TaskMatrix is doing. Yeah, any questions on this model so far? All right.
What do you mean by API can learn?
Oh, okay. So the API will know what are the different contexts it was used for, and whether or not the user reports that their output is acceptable or not. Like after a sequence of APIs, the user can like maybe put a thumbs up or thumbs down saying whether the response was good. So if the response was bad, then this will go to the API developers to let the API developers know that, you know, this is use case failed. Okay, this may also be done in an automated way, actually. Like you can treat this feedback as some form of database, and then you can run like some form of learning algorithm to update your API based on what works and what didn't work. Yeah, so this is still like under wraps. They didn't release the source code for this yet, but I quite like this idea that you can learn. Right, Terry, you got anything else you want to clarify?
That's all for now.
Okay, all right, let's move on. All right, so this is just some example I just want to like show you all because I found it's quite cool. One of them is PowerPoint slide creation. I can't wait for this to happen. You know, after Microsoft bought OpenAI, okay, they didn't buy OpenAI, but they had they like collaborated and had some shares. Okay, one thing they are working on is to use ChatGPT into Microsoft Office products like PowerPoint. So you can see like these are the APIs, like select title, insert text, basically the functions that you can do to perform some operations on your PowerPoint. These are your APIs, and you can interface this task matrix with a PowerPoint API, and you can get like this kind of PowerPoint slides with this kind of prompt. Like fill in the title in first page with big technical companies. Yeah, this kind of prompt you can already get the slides. And then you can like, this is very rudimentary. I mean, like I expect more of it. Like I expect it to do image as well on the slide. And maybe next time my slides can be done with a prompt. Yeah. So yeah, I'm quite looking forward to this slide creation. There's a lot more examples in the paper. I just pick out these two because I think these two are quite cool. Like the other one is a smart home. Like imagine you just talk to your phone, like say, oh, wake me up at 7 a.m., do something for me. You know, you can even do an if else rule here. And then like you can play music by calling an API called play music. All right. Then you can even ask like a robot to help you get a cup of milk from your fridge. All right. And the robot will then do like, you know, the pick place API that I went through in Second. You can also do that by calling the API. So because you want to do this task, you can then call this API. Okay, one thing to note is that because you want to interface with millions of APIs, you kind of need to filter the APIs that are relevant for your tasks, right? So maybe each API could have some form of tag, saying, oh, this is a robot, this is for text, this is for vision, this is for video, this is for image. Then when you choose the API, you can choose in a more condensed way. So that's things that could be done to help the model know which API to do. So this one, you don't need to put inside GPT. You can do it as an external filter. All right. So before I open for questions, I just want to go through the main advancement I thought was quite cool. And that advancement is called HuggingGPT. So I think this HuggingGPT and the earlier one is quite similar. The only difference is that instead of APIs that we cannot access, HuggingGPT will be made open source, and the APIs are actually HuggingFace models. So whatever models you see on HuggingFace, like image segmentation, image bounding box selection, audio processing APIs, all this can be used. So this model will be open source. The only thing you need to know or need to use is this like ChatGPT. You can use GPT-4 or GPT-3. I don't know if you can use a HuggingFace model for this. Okay, they haven't open sourced the code yet. But this one, if you can get everything open source and you can even use like HuggingFace model to get the LLM running, this essentially will be done for free. So this is like visual ChatGPT, but instead of using paid API, everything is like HuggingFace APIs, which are free. All right. So the key thing to take note for HuggingGPT is similar to the TaskMatrix. It breaks down a complex task into subtasks. So it's the same thing. You have a solution outline. You don't have to do it iteratively anymore, like what you do in Visual ChatGPT. You do a solution outline, and then you let, okay, so the first part is the solution outline, task planning. Okay, based on the prompt, give the solutions. After that, each single part of the task, you select a model that is most relevant for it. Then after that, you execute the models, and then you combine them together to generate the response. So that is more or less the workflow. I will go in detail in the next slide. So you can see over here, this is like describe what this picture depicts and count how many objects in the picture. So the first thing is maybe find the bounding box for what are the animals, and then like you can call the various API, like this is the description API, image QA or image description. And then you can go to like bounding box detection. You can get a giraffe, zebra, zebra, giraffe, zebra. So the model can even tell you it has generated bounding box, did image classification, and basically give you the final result, which is this one. Yeah. So I think what is lacking is like count how many objects. You still have one more step to say that you have 5 objects. Oh, okay, it's already here. All right. So using this, you can get all this done. All right. So I will go through the details in the next slide. So this is the part that this HuggingGPT, or what Andre Karpathy calls JARVIS. I quite like the name JARVIS because there's something like I want to create as well. All right. So what they do for the first part, task planning, is to basically put a whole like solution list of like what is the sequence to be done. So the input will be the user's request. The output will be the expected task sequence. And what is cool is that you don't let the model, you don't even need fine tuning. What you need to do is to have a database of memory. I like this part also, memory database. And based on the user's input, you retrieve semantically similar input-output pairs to let the model use it as a few shot example. So this helps the model learn, okay, through the in-context prompt. It learns what are the solution steps that are most likely to be used, because you can, like maybe from a vector database, you find the most similar input-output pairs, and then you let the model learn few shot. I think this is the future, actually. You first retrieve from memory the relevant stuff for your tasks. Then you use this as few shot prompting for GPT models to know what to generate. So I've tried it out actually off screen. I mean, I can show you all later the GPT, no, I mean the GPT-4 that I asked it to sample from memory some state action transitions, and it works surprisingly well. So I think this is really the next step. The next model selection, as I said earlier, you filter the models based on task type like text, image, and so on. And another interesting thing is they rank this API, all right, by the number of stars on HuggingFace. So if you create a model on HuggingFace and you have a lot of stars, chances are HuggingGPT would select you. So I also like this a lot. So, I mean, kudos to Andre Karpathy and team who did this. Okay, I'm not really sure if it's Andre Karpathy. His name wasn't on the paper, but I assume it is because he mentioned a lot on his tweets that he's creating JARVIS. So this rank by number of stars on HuggingFace is very good because it induces competition between APIs. And then every time you have an API that wins, you know, that API will be used more often. So this reminds me of this thing called neuro-Darwinism. Okay, this is by Edelman. Eric Edelman. Yeah, we can go and Google him. Yeah, he's saying that there's groups of neurons already present in the brain, and what the brain needs to do is to just select which group of neurons to use for each task by some form of natural selection. And this idea I really like a lot. Actually, I like this whole architecture a lot in HuggingGPT. So yeah, we can discuss more about this later. Later, the next step is task execution, which is executing each invoked model from this model selection state and return all these results to ChatGPT. And ChatGPT will then use all this to integrate the prediction of all models. So this, okay, before I move on, I will take some questions here. Anyone wants to ask anything about HuggingGPT?
One question regarding your comment on neural Darwinism. How is it different, or is it similar idea as I think it's called lottery hypothesis?
Lottery ticket hypothesis, is it?
Yes.
Okay, lottery ticket hypothesis is by Jonathan Frankel. He basically says that every neural network has a winning subset of neurons that will be activated, and you can then sort of prune to find the winning connections. But maybe this is the winning network will already be there. All right, so this is specific to maybe just one single network because you only want to find one. But in the Edelman's one, what you are actually finding is you are actually finding a subset of networks for different tasks. So maybe this network maybe is for task 1, and then you have a separate network here for task 2. So this considers multiple tasks, and then each neuron group will be selected for that particular task more and more in the future if it performed well before. So the difference is the neural Darwinism is for multitask. At least that's
so
why
it's like a generalization of lottery ticket hypothesis.
Slightly different also, because lottery ticket
not
hypothesis is more to train the network and find the right connections. The neural Darwinism is we just assume that all the connections are already sort of trained, or rather random connections also can work, and then you already can find a random group. I guess it's similar in some sense because you already say that there's some group that works, group of neurons.
Yeah, in the former, for a fixed task, you select the most relevant bunch of neurons. In this one, for different tasks, you select the most relevant bunch of neurons, right?
Yeah, I guess you can treat it that way.
Okay.
Yeah. Yeah, Dylan, you want to ask something?
No. I was just trying to say that there were some similarities, something similar to what you were saying about neural Darwinism and lottery ticket hypothesis. There is some similarities, but it's not exactly equivalent.
Yeah, I really like all this neural Darwinism thing. I even bought the book called The Mindful Brain. Yeah. So right now, actually, is a slightly different parallel because we are linking this neuronal group to an API. Right. Right now, the APIs are fixed and unlearnable, but if we can imbue it with some learning signal, like what you saw in the TaskMatrix.AI, you could make the APIs learnable, and that is very enticing because then you could have a potentially learning system. Yeah. In fact, I believe one way to make you can even make the meta process learnable, which is this task planning process learnable using memory. This memory, if you change the memory accordingly, you can. So memory will help to learn the meta task learning, where you will learn the meta.
Really, they are not exactly learnable in the sense that it's adapting on the online data, right? It's just there is a feedback.
You could make it online memory. The memory could be dynamic. You could have a dynamic memory base in some cloud service that keeps getting updated with new requests. And then you could do some form of memory selection to select the most diverse memories or something and throw away similar memories. Yeah, so that when next time someone queries the memory database, you will return quite diverse selection. Yeah, you could do something like that. So in some sense, this memory is a learnable online one. You can easily program it to be such.
What is the memory used for again?
The memory is used for for example, if you have an input task saying that count the number of animals. So in the past, maybe someone has done this kind of thing before. They have done a selection of input is count the number of balls. or input, count the number of clouds. So you see, when you want to count all this, maybe the output is similar. The output will be, bounding box, then you count bounding boxes. So the solution steps are similar. By giving the few short examples here of all these previous examples you use, you are sort of like grounding the model on past experience. And so the model is able to output the list of things that could potentially help with this new situation. So it's like referencing memory to find the more semantically related. So how do we encode this thing in semantics? One way is to use like OpenAI embeddings. Yeah, so I will actually cover embeddings next week. So one way is to use embeddings. It's really very cool because the way you can encode similarity, you don't use like TF-IDF or TF-IDF, which is like using word counts anymore. You can just directly go to semantics, which is like the semantics of the entire sentence. Yeah, of course, when I was thinking of memory, I was thinking more of like abstraction space in terms of the vector space. But if you could phrase everything in words, you can get your abstraction space in words. And then from these words, use some embedding mapping to a vector space, like the OpenAI embeddings. So yeah, it's quite cool how you can actually do memory retrieval with vector similarity to like select the most relevant memories.
And that's what ChatGPT is doing here, right?
It isn't doing the embeddings part yet. The embeddings is talking about retrieval from memory. That is a separate mechanism. What ChatGPT is doing is converting tokens into its embedding space. That one is done by the transformer model. But the embeddings I'm talking about here is document retrieval, memory retrieval. Is the embedding that you give to like a particular paragraph or particular text in the PDF or your paper, and then you can get your memory to retrieve that relevant paragraph.
So
Okay,
what's the purpose of the memory? Why do you bring up memory in here again?
The memory is so that the model or ChatGPT is able to learn the solution steps to output. Like to count the number of animals, it needs to know, okay, go to use a bounding box API, then do a counting API. And all this, if you don't give it some examples, it can hallucinate and give random garbage out. But if you give it the right examples, you can potentially few short learn from your examples, and this will give a very accurate output for your model.
But I guess you're suggesting one way to ensure that the ChatGPT doesn't hallucinate is via this memory mechanism, is it?
Yes, and not just doesn't hallucinate, you also give it the right examples in its past experiences in order for it to like adapt few shot to a new experience. It's very powerful because you are no longer just learning from scratch. You have some prior knowledge. You can retrieve the relevant prior knowledge to solve a new task.
But within this, like for example, count the number of balls, count the number of clouds, ChatGPT on its own, it's able to really thematically process into the separate subtasks, right?
It may not, because you are asking for a list of solution tasks, solution steps, which may not be in the training set. You see, your training set maybe doesn't include like step 1, do bounding boxes, step 2, count. Yeah, this may not be present in the model training data. So this might be, you might ask it to do something completely different. Like if you have a drone, ask it to fly up, fly left, fly right, those kind of solution steps are domain specific. So it is best if you give it some examples so that it knows like what are the kind of actions it can do. Of course, there's also like, you could also give like a list of, you can also give a list of possible, subtasks or steps, and then ask it to choose. So because GPT kind of understands meaning of like certain subtasks, is able to like see like, okay, this subtask should fit after this, natively it can do that already. But if you give it input output examples, it will do it even better. Okay. Yeah, I mean, we can discuss more about this in the next session, because we are talking about retrieval, memory retrieval next session, and vector databases. All right, can I move on? Because I have quite a lot,
Yeah,
a lot
please
of stuff to cover as well. So this is the prompt for task planning. So you can see that, like even for Visual ChatGPT, all you need to do is to tell the model what are you are able to pass user input to several tasks in this format. And then these are the description of the format. And then you must select the task from this task list. All right. So that's what I was saying just now. Okay. And then if you cannot do it, you must reply empty JSON. That's like the failure case, so that you let the user know this is not possible. All right. Here are several cases. These are the demonstrations from Memory. I really like this. I mean, if Andre Karpathy was one doing this, I can see great future in this approach. Yeah, I really like this a lot. Yeah. In fact, my research for learning fast and slow, I'm trying to migrate it to using GPT-4 as well, because I think this dynamic adaptive system works very well hand in hand with GPT-4. All right. So let's talk about this. This is the chat history of the previous, like the user interaction, like AI human. You can talk, because this is not just one instance. You also want to give it previous grounding of the conversation. All right. So this is the thing, like these are the demonstrations of the tasks. So like maybe the task itself is about counting the number of bounding boxes. So you retrieve, like in the past, people have told you this task before, people have told you this task, people have told you this task. And this one is like the 3 different tasks. And then these are the solution steps. Like first step is image to text. Second step is object detection, and so on. This one, you can see the first task is this, second task is this, third task is this, fourth task is this, and fifth task is this. And fourth task is like, yeah. So this is actually very cool, because, you know, in the learning fast and slow architecture that I was trying to develop, I was also thinking you can ground your goal as a subtask. Okay, and you can use a language model from the big task, generate your subtask, and then from your subtask, you can head towards the subtask through some goal-directed learning. And in this case, to head towards the subtask, we don't even need to learn anything. We can just use a pre-trained API. So I find this way of like LLMs as a task to subtask planner, and then matching the relevant APIs to solve the relevant subtasks, I find this approach very promising. All right. So this is the task planning prompt. The next is how the model generates the model selection. All right. So model selection, what you can do is you can, again, give it a prompt, say the AI assistant outputs model ID of the most appropriate model, you know, and even can give a reason for the choice. Interesting, right? You can ask the model, why do you choose this particular API? All right, then these are the candidate models. And just to highlight this candidate model here, all you need to do is to give it like the ID number, the metadata, which is like what it takes in, what is output, right? And then the description of what it is. So you don't even need to give the input-output examples. You just need to give a description. And from this description, GPT is able to choose what model to use. Of course, before we give it this, remember last time I was talking about you filter by data type. So like you obviously only give a text-based model for a text-based kind of interpretation, and you give like a image-based model for an image-based task. So you really can narrow the selection of models, because you know you have 32,000 contexts for your memory. You don't want to exceed it. So this is what you do. And then what you do next is you filter, or you order by number of stars, like how competent the model is, and is gauged by the number of stars. Like the more stars your model receives on HuggingFace, the more competent it is. And I think that is correct. Yeah, I mean, you're letting the community vote. So whoever came up with this really is quite genius. Huh? I really like this a lot. Next, we have this response generation. So after you have gotten your models to choose to run, you can actually run them in parallel if they are not like in a sequence. So the beauty of this model selection is you can also say that what sequence are you doing it in. Like from your model list, you can also specify, is it sequential or is it parallel? You can run all the parallel together, then you do the sequential one in sequence. After that, you can basically just put all together. So this response generation, you tell the model what to output. So with this inference results, okay, you need to describe the process and the results. So you must first answer the user's request in a straightforward manner. Means you must tell the user like how many animals are there in the picture. Then you must straight away tell. So GPT will output, there are 5 animals in the picture. Okay, then after that, GPT will then say, oh, what did I do? I went to do the bounding box API. Then I went to, these are the bounding box classification, what do you call that? Probabilities, or or basically what is the model's output predictions. Yeah. So you can actually tell the user in a very clear-cut manner. So it's like a very like explainable way. So you can see over here, this is, you tell the user what is the image about and straight away answer the question. And then these are the steps that the model takes what did the model do to get the results for you. Everything is very explainable, and you know, okay, exactly which API it did. And you know, you can even tell you the reason for doing so, okay, because you have prompted the LLM to generate the reason. Over here, look at this reason, your detailed reason for the choice. So you already know why the model selected it. This can then be used to give you the response generation over here. So this model came out very, very recently. I think it's also on 28 March, but I heard about it only like 2 days ago. So I can tell you the field is moving very fast. I mean, what used to take months of innovation is now happening in days or weeks. So we can expect to see better and better models. We don't even need to improve GPT-4. We just need to improve the way we prompt it. We need to improve like maybe how we interact with GPT-4 in a like recurrent or hierarchical layer. You know, you can already get advancements from it. So I'm quite optimistic for this. All right, so this is another example to just show you, like based on the post image of this example and the description of this example, generate a new image. So you want to generate like, so what you do is you will like take the post of the first image, all right, and then the description of the second image is basically you need to find out like what is the second one, which is young boy riding a bike with a basket. And then what you need to do next is you need to generate the picture of the young boy in the bike in this kind of pose. So they basically just use the pose over here, open pose text to image. Yeah, so this is the model use, and you can get this final image. I mean, it's not exactly in the same direction, but pose is similar. I mean, he's holding the hand up. So this is exactly what this HuggingGPT or JARVIS can do. So we will get the open source code soon. I hope to try it out. I'm very excited to try this out. It's even more powerful than visual ChatGPT because it has audio and video as well. You can use any HuggingFace model to do your processing. And what's even more cool about this is that if you interface your request over here using like Whisper from OpenAI or some other like speech to text, you can talk to your assistant. Your assistant can do it, and then you can just use a text to speech, and then your assistant can like reply back to you in voice. So this all can be done like right now already. That's why I say we can create JARVIS right now. We just need to have some money because like in order to get the speech to text, you need to pay like 2 cents for Whisper. Then to get the response, maybe you need to pay 2 cents for ChatGPT, and to get the speech to text, maybe that's free. Okay. In fact, Whisper is open source, so you can actually do it for free as well. So maybe you just need to pay 2 cents for this. And then like the HuggingFace API models are all free. So yeah, 2 cents per request. I don't know. Will you pay for it? 2 cents per request if you can create a personal assistant for yourself? Like every time you talk to you, you need to pay 2 cents. Will you use it? I mean, y'all can answer now. Oh, is it enticing if you can generate this kind of personal assistant to help you do stuff just for 2 cents every prompt?
2 cents sounds a bit much, you know. But I guess if you are a large scale business and it's a required pipeline to actually expedite, then maybe it could be worthwhile.
Yeah, personally, I think it's okay to use for like difficult tasks, but I think for the average user, if you use 2 cents per request, like you imagine you ask it like maybe 30 requests per minute per hour, one day. So 30 requests is about 60 cents. So like one day, maybe 10 hours is $6, 600 cents. Yeah, $6 a day. 1 month is $180. I think it's decent. I mean, if let's say the output really helps you a lot. So
could be really useful for like, for example, outsourcing a way to like automate the labeling of unlabeled data, for example, maybe.
Yeah, maybe. Yeah, actually, I tried GPT for labeling of data. You just need to give it like a few examples of previous data. like you can give it in this example. Let me just write it out here. So you can give, this is very cool because you can just give it like that. Let's say if you can give it in terms of like text. So you can give like that, category A, description what, category B, you give it a few, hopefully it fits within your prompt limit. Okay, if not, we have to talk about how we can extend the prompt limits, which is what the next part of this presentation will talk about, the memory part. Then you can ask like description, like ZZ, what is the category? And I find that this actually works quite well because even if I have some noise in the above categories, I want to try like even odd numbers, the classification category. If I were to label an odd number as an even number for one of this, like earlier a few short description here, somehow it's able to get the majority class right. So it's quite robust to noise. So GPT can do few short classification that is quite robust to noise. And I feel like that could potentially help with labeling a large kind of data set by just giving a few short examples, and then you can label a lot more examples. You can label like description, like, yeah. So the only limit is how much money you have to pay for the model, because, you know, if your description already takes up 32,000 context length, like those kind of medical data sets, you have a long time sequence, you know, you probably can't give it like this amount of supervised learning data before that. You probably need to do some fine tuning, which is not possible yet. Yeah, but suppose that if your data can be fit into the in context prompting, you can actually label this quite efficiently. Hopefully your description is very short, because if not, you will use a lot of tokens. Yeah, GPT with the attention mechanism is a very good few short labeler. This is my experience. Yeah, in fact, you can even label 0 shot. You just need to give the description, like what you're doing for this APIs. You're just giving the description of the API. You can sort of choose the relevant API for your task already. And that is really amazing. Yeah, that really just shows that the attention mechanism is performing well. Yeah, I'm quite impressed with GPT-4. I tried it out, and I feel like it's able to do a lot of very generic tasks. So I'm quite optimistic about the future of this. Although I actually have like a short video talking about like whether it will reach like AGI or like ASI, artificial super intelligence. I don't think this will reach it, but it will already match the performance of most humans because of the way it's doing attention on a human labeled data set, on human data sets across the web. Yeah. Maybe we can like ask like 1 or 2 more questions before I move on. You have anything else you want to talk about?
No, because you were talking about medical data sets, so I was wondering whether to ask or not. But you were mentioning that time series data of very long time steps is very difficult for it because it has not enough memory, right? I don't think it's just that issue. Are you even sure that it can take a normal time series and do any kind of classification? I'm not so sure about that. That's one thing. And second thing is about, I mean, I have no doubt that it can do well for generic tasks that it has already seen in its training data. For example, your usual NLP task, sentiment analysis, all this, I think it can do it. But if it's something that's more specialized and requires specialized knowledge like that, for medical data sets, right? Like for example, if you want to label images of X-rays, then I think it might have a bigger problem with that. Any thoughts about that?
Yeah, I mean, currently the image modality to text needs some improvement, because like you can't possibly write your text in terms image in terms of text. You need a visual language model where you process the data, and the visual language model will then output it in terms of like text. Yeah, so
even for medical text, I think you will also have problems. That's my point.
Correct.
When the task is very specialized, it will have problems. It can only do well for generic tasks.
Yeah,
that's not true, right? The assessment.
Why is that not true?
Sorry, we cannot hear you if you are speaking. Right.
Oh, what happened? I tapped off for a bit.
Did he drop out?
I don't know. He's still there.
What was the question?
No, I was saying that the model will find it hard for specialized tasks like medical text classification. And so he was saying that it's not correct, and then he dropped. So it's like hanging. It's like a cliffhanger.
I do agree that for specialized models, the GPT-4 performance may not be that great, because is not specially tuned on that data set. Yeah, like Christina said in the comments also that she tried on law data sets, it didn't work too well. Okay, but I would like to say that as the model improves, like GPT-5, GPT-6, maybe you don't need a specialized medical data set anymore, because as long as the training examples are more for that kind of domain, it might be already proficient at that kind of domains as well.
To a certain extent, I think you can use few-shot learning to tune the model. Yeah.
Correct. But then there will be a limit of the memory context length, which is a very big problem. I will be spending some slides on that later.
Yeah, another thing I want to add is about, you were talking about visual inputs. If I'm not mistaken, what was that? GPT-4 already has multimodality built into it. I might be mistaken on that, but I thought I saw something along those lines.
Yeah.
Is it? I'm not too sure. GPT-4 seems to be able to take in images as well.
Correct. So the GPT-4 exact architecture, we don't know yet because they haven't released the visual modality. But if it's something like visual ChatGPT, then the image processing, all this is done by APIs. It's not done by a separate language model. So essentially, you only have one language model, which is like ChatGPT, to handle all modalities. It's just that the APIs will do the processing for non-text modalities. Yeah, so it's like what we see here in this slide. Right? You can give it images and the HuggingFace models can sort of process it.
Or is it based on clip embeddings to generate text from the images, or how does it do it?
As a question answer kind of model where you can ask questions and based on, I believe is run on clip. Yeah. You need to convert the image back to like same embedding space as text. So I believe a clip-like embedding is used.
Yeah, I got it. Thank you.
Yeah, that I'm not too sure. I have to go and check again the question answering API, how they do it, but it makes sense to use clip. Yeah. All right, so let's talk about the future. All right, so how can LLMs be used not just as one LLM, but as a system of LLMs, a system whereby they can feedback and influence each other. So this is very cool because, you know, in society, humans, we are only as smart as the group we are in. All right, so somehow in groups, we can emerge intelligence that one single person may not be able to do. And you can see with the internet, with social media, we have been creating AI advances so fast because everyone is like building off each other. Like I'm going to build off like the work that GPT-4 is doing for my next research, and like people might build off my ideas and so on. So we can also imbue this form of like society of mind kind of thing like Marvin Minsky was talking about. Like you can build a group of agents that can like learn from each other, can interact with each other, and maybe you have emergent intelligence that is greater than the sum of its parts. So this is quite cool. And I think this area is ripe for research right now because GPT-4 is so powerful. You can use it as a cluster of agents. And this, I think if anything achieves AGI, it will be this kind of structure, like multi-agent structure. Yeah, I don't think like you can use like reinforcement learning techniques to improve GPT-4 like iteratively. It's just too difficult to do reinforcement learning on an open-ended domain. But if you do this society of minds thing, it might potentially achieve AGI. So this is my take on AGI. This might achieve it. Okay, so let's talk about the first thing, hierarchical learning. So this is very much based on the brain. You know, like in the brain, you have like neurons that send stuff from the bottom layers to the top layers. So this is the traditional approach where we do the feed-forward layers. Okay, but there's also this thing called feedback layers in the brain where your top layers can sort of constrain the bottom layers. In fact, people have said that there might be as many as 10 times the feedback connections as feed-forward. Right now in deep learning, we only model the feed-forward networks, feed-forward connection. Okay, but I mean, in one of the other things we talk about memory, actually the feedback connection here, I realize is also modeled in transformers. Okay, because transformers has a skip connection. So you can actually use the output of the next layer to like sort of influence the first layer as well. So this is my theory, okay? The feedback can be modeled by multi-layer transformers. Because like you can give it a goal and then sort of you can constrain on that goal. So there must be some form of feedback already. So yeah, but now I'm not talking about one single model. I'm talking about multiple models. So like, for example, you have LLMs with tools or LLMs with APIs. The bottom layer can feed information to the top layer. Top layer then can constrain the bottom layer in generating the right response. So this can be like a content generator at the bottom, and top layer can be like a fact checker. So this could be something like you want to find sources in a search engine. The top layer will then, based on like the web pages that it has found, to constrain, to give some context to the model. So you can tell it like, these are some context that you need to follow. So memory 1 is this, memory 2 is this, memory 3 is this, and generate. Yeah, so you can constrain using memory. So this top layer can give you the memory or the fact checking or retrieval from valid databases. And then you can use that as few-shot prompting to constrain the bottom model here, all right, to generate the text. And people have found that it works quite well, constraining by few-shot examples. And one thing to note is that this model at the top and this model at the bottom actually can be the same model. You're just calling the model like different times. Yeah, in fact, you know, when OpenAI did like that, like maybe ethical filter where you say that, oh, you don't want to talk about violence, don't talk about sexual stuff. You know, some people have tried to jailbreak ChatGPT, okay? Maybe some is an understatement. I think a lot of people have tried to jailbreak ChatGPT. So if the ethical filter is at the layer, whereby it's at the bottom here where the user can actually jailbreak it, okay, what we will find is that we will be able to jailbreak quite easily. Okay, what I suspect, okay, because they didn't release the model, what I suspect is that the ethical filter here is done at the top layer. Okay, so there's a filter API and so on. So this is done like after the base model generates some output, you have the filter to like make sure that the output is moderated. So the filter is beyond the user's control. So the user cannot jailbreak it. So this is what I suspect is happening. So the top layer may not be LLMs. The top layer can be some moderator, like some prefrontal lobe or something to prevent bad data from generating. Yeah, so this kind of hierarchical structure is very useful. Like for visual ChatGPT, the top layer is the prompt manager that helps to process multimodal input, and the bottom layer will then be the GPT layer that sort of generates like, do you need to use a tool and so on. Yeah. And for like TaskMatrix.AI and JARVIS or HuggingGPT, the top layer will be like the task list or the sub task list, which is like what are the steps to take. And over here, this can be like execute the steps and then combine output together. So as I said, this can actually be the same model. You just need to do it in an iterative manner. Like you first generate the top part, then you use the top part to constrain the bottom part's generation. Or you can use this top part, which is the subtask list. Then you can do some rule-based filtering. You can also do some rule-based thing. And then you can then give it to the bottom part. Yeah, there's many possibilities for this. People are experimenting with a lot of things. In fact, there's also one thing to take note, all right? So apart from all this that I talked about in the slide, recently I've heard of this system called reflection. How many of y'all have heard of this reflection? The X is a capital X. Anyone heard of this model before? Okay, so let me just explain this model. This model is a model whereby it does a certain task.
Improving one, is it?
Say again. So can you say that again?
Self-improving.
Ah, yes, self-improving, correct. So I'm skeptical about self-improving, but it does solve tasks better. So what it does is it does the task, then you ask it to reflect on its actions, and then do tasks again. So given the reflection as the grounding, all right, it can somehow solve the task like 30 to 40% more based on some like text-based RPG will, like, just by asking it to reflect on, like, if it didn't solve the task, why did it not solve it? And you can say, oh, I didn't solve it because I didn't find the lamp first. I should find the lamp, that I take the mark. Yeah, so something like that. You ask it to reflect, and then somehow using that as, so what my thinking is that this reflection here will form a grounding or sub goal. And then once you use this to do the task again, because you have this as a sub goal or grounding, you are able to sort of constrain the generation such that, you know, it's something like having some higher guidance to tell you, okay, you need to do step 1, step 2, step 3. Then when you do the task again with this step 1, step 2, step 3, you can do the task better. So this also reminds me of other methods like chain of thought, whereby you can ask it like, what should it do? or ask it to explain. Yeah, so it somehow, it actually is quite amazing because like models like this works like pretty much like children. Like you can ask them, why do you think you did wrongly? Or what do you think you should do? Then you think, oh yeah, I should, in order to get the candy, I need to climb on the stairs. I need to reach onto the shelf and get the candy down. So then they say, yes, okay, that's very good. Why don't you try it out? Then the model somehow can perform better than if you didn't ask it to like think about it. So it actually is quite relatable to humans because like we also need some form of prompting sometimes, like to solve a difficult problem, and someone need to prompt you. So how can we do it differently? So how should we break this down? So by some step-by-step guidance, you're able to generate the solution better. And this step-by-step guidance can be the top layer. So like chain of thought, this can be the top layer guiding you, and then the bottom layer will then execute what is being taught out. So there's many approaches to view this hierarchical learning, and these are just some of them. Maybe I just take a quick pause here. Anyone else has any like things that they have heard of that can fit into this kind of context of hierarchical learning? Okay, if not, we will move on. All right, the next thing I want to talk about is recurrent hierarchical learning or recurrent processing. Okay, take a look at this video here. So you have a few language models, a visual language model, audio language model. The visual says that it sees like car and sofa, and the audio says it hears a room. And then so like you ask the model to say, based on this, what do I see? Oh, I see these few things. And then you can ask the model again, what do you think you might be doing based on what you see? And then you can say that, oh, I'm watching Formula One. So this is called Socratic Models. I used to be skeptical of this model because I think that it will take a lot of tokens to like sort of learn. But after seeing all the chain of thought prompting, reflection, and so on, I think prompting makes a big difference to the performance of the model because you can ground it in some facts at the past like this. So because of all these things that you ask the model, what do you think you see? What do you think you hear? Okay, what do you think it might be? What do you think you are doing? So by doing a step-by-step like that, you can sort of discuss about what is happening right now and come to a conclusion, okay, which is a difficult conclusion to come to if you straight away just jump to the conclusion straight away. So there's some form of communication between the various modalities, and then eventually you come to a conclusion. So if you all heard of Jeff Hawkins on intelligence or like the book called Thousand Brains Theory, he also talks about cortical columns, the neocortex columns, voting with each other. And this voting leads to a joint decision. So I'm thinking actually this sounds quite similar to this process. I mean, although it's not in neural impulses, we're using words. But in my own opinion, as long as it works, we don't have to go to the impulse level. If words work, just use words. All right, the main idea is what is delivered. So as long as you can reach the outcome, I'm fine with whatever means you use it. Okay, I'm not a brain modeling like enthusiast. I'm more interested in getting what the brain uses and modeling out in systems. So if this kind of text works already, why reinvent the wheel for neural impulses? Just use text and word embeddings, right? It's already being studied quite a lot now. So this is a pretty cool thing. Like this recurrent like interpretation of like your results. Okay, this is quite cool because it can sort of mimic consciousness. Like when I know that I'm in the room right now, I'm talking to you, maybe like the visual side, I see that I'm in a room. The audio side hears that, there's no noise around me. Yeah, then maybe I come to a realization from the combination of my senses that I'm in this particular position. So yeah, that's recurrent processing. And I think if you combine them, this recurrent as well as the hierarchical, you get the hierarchical recurrent processing, which is like similar to what Jeff Hawkins talked about on intelligence, like hierarchical temporal memory. Okay, although he has moved away from the hierarchical part, he says that there's only like maybe 2 hierarchies in the brain. I still think hierarchical grounding is very important, as what we've seen earlier, like the top layer can ground the bottom layer. Memory, maybe you can treat the top layer as memory. Memory can ground your generation. Yeah, together with this one, where you can talk about things from different angles. Like you can maybe ask the LLM to give you the response based on approach 1, approach 2, approach 3, approach 4, and then you can ask the LLM, combining all 4 approaches, what do you think you are doing? Yeah, so this kind of recurrent processing from the same model or from different modalities is very powerful, because in this paper, Socratic models, they actually achieve great performance just by doing like this kind of few shot prompting without even fine-tuning the models itself. You don't have to fine-tune the weights at all. The models can be their original weights. You just need to give it the right context, and it can sort of really do things that it cannot do with just one single model. Yeah. Any questions on this? Okay, if not,
maybe one question from me. I might have missed this, but I was wondering whether you have any idea of why chain of thought prompting works so well. I mean, why can't the model just, I don't know, do chain of thought internally? Yeah, when it comes up with a prediction, but why do you have to actually explicitly ask it to explain itself in order to get a better performance? So why does chain of thought actually work well? Do you have any idea?
actually, the intuition is quite simple. I mean, at least my intuition. Say this is your original prompt. Okay, let's say this is the prompt. The prompt itself maybe doesn't contain, like, if you ask it to calculate my 5 plus 5, maybe it doesn't contain like how to calculate it. So then it needs to go by association, you see. It needs to go into its like weights and then see like based on probability whether this one is a 10. Okay, so if this happened in the training set, no problem. Then you just need to have the prompt and then your answer will straight away be 10. Like 1 plus 1 equals 2. Like, yeah, but if you come out with some obscure number, it's not in the training set, okay, then you need to know like how is this like calculated. So then you can use chain of thought to ask it like to explain. So this explain part can be like, I initially have the number 5. Like maybe you can explain like, I have a number 5. I add 5 to it. And I get 10, something like that. So by explaining the process, you are actually asking it to explain the procedure. So, you know, in humans, we actually generalize not because of memorizing certain input output. I mean, that happens sometimes.
Yeah,
but
I know.
sometimes you generalize by procedure.
I know. I mean, humans, we generalize in the sense that we know of rules like addition rules, subtraction rules, and so on. But neural networks, they don't really have this set of implicit rules that's inbuilt into the model. Or they are just mapping an input to a set of outputs only. So I'm still thinking of why is it that the very fact that you ask a neural network to explain itself leads to a better performance.
It gives it more context actually. So like if you ask it to explain itself, like the addition part will be explained, and then you can ground the generation on this addition part. So it is more able to.
The neural network also doesn't know how to explain. This is a language model. It doesn't know how to add, right? It doesn't know how to add. I mean, it's not a calculator.
Yeah, so this thing normally what is done is like you can have some fine tuning or few shot prompting to tell it like these are what you should do, and then by asking to explain, you can get it to get the right explanation out.
Still not sure they understand this, but okay, it's okay.
Yeah, chain of thought. Yeah, sorry.
I have some thought on this same issue. So, when you say the model does not understand what addition means, you are saying we didn't hard code the addition rule. But you see, but you see, I don't think I actually also we didn't hard code the addition in our brain, right?
Yeah. But we memorize multiplication tables.
Yeah, but so we follow this rule. This is like not a very, from my understanding, it's like not a very low level rule. It's a rule at a very high level. That's why even for us when we do calculation, we also can make mistakes. But the thing is, if you elicit the step by steps thing, right? My guess is the model is trying to approximate the rule. Although it does not really know the rule, but it's trying to approximate the rule. And it's still true that when you break down the steps, it's easier to approximate. I think Toming did the experiment prime number, right? The video.
Yeah,
I watched the video.
numbers, yes.
So if you asked it, it's going to be very hard. So I think it only interpolate between the answer it can find online, which is the nice one, right?
5,000 prime number,
yeah,
10,000 prime
so
number.
so the same thing is I think the reason why they get it wrong is you didn't like do the prompting, the chain of thought to like make it reason step by steps. So if you break down, then it won't try to extrapolate from the existing answer because that's going to be not accurate. But if you are going to break down the steps, it can approximate each step, which is much easier. So that's my I don't have anything to back up. It's just how I feel about this.
It's quite cool actually. Like you can just ask the model to reflect on its errors, and then it can use that to generate the right answer. For some, I would like to emphasize for some contexts, because if you can do for all, then I would say that this is AGI already. You can just ask it to self-improve. But my experiments have shown that it cannot. Yeah.
I was just thinking about Zhe's answer, and I was just thinking that actually when you say that, I agree that the model is doing some kind of approximation and interpolation, but I also think that humans do learn a set of rules. Let's say for addition, right? I mean, we know like 1 + 8 at the very ground level, because we count, right? We have 10 fingers and we can count. But at a higher level where let's say we were to add like two-digit numbers or 3-digit numbers, then we have a set of rules to help us in doing so, right? We have our addition table, you know, where you carry 1 to the 10th digit, that kind of thing. So these are rules that actually we learn from primary school, but the model does not learn that. You see, the model is learning a set of, all it is seeing a lot of sets of numbers being added together. Some can be added correctly, some can be added wrongly. So it's kind of like unsupervised learning in that sense. How does it know how to add in this sense? Now I think it also can be done.
I think it also can be done through interpolation, because in the training data, I believe there's many examples of doing elementary addition. So they can kind of mimic.
Yeah, maybe if you have enough examples that are correct.
So it didn't really learn the rule, but yeah.
It looks like it learned the rule.
It is just my guess. So
I get what you mean. It looks like it has learned the rule, and it can do so if it has seen enough correct examples. Yeah, in the billions or something. Yeah.
So actually, chain of thought can be treated in some sense as generalization, because you don't generalize from the character level now or token level. You generalize at the procedure level, or you give it some grounding, some sub goal it needs to do, which is pretty amazing. You can query the model. Okay, what's your sub goal, or what do you think you should do? And then that what do you think you should do can be like step 1, I should do this, step 2, I should do this, step 3, I should do this. Then you can just say, okay, based on what you think, execute it. So in some sense, it's giving some form of grounding, which if you didn't ask it to begin with, it will be very difficult just from next token prediction to do it. So at least you have some form of grounding, it will be more accurate. So yeah, chain of thought does have its use. Okay, let's move on. Okay, memory. Okay, this part I will just touch and go because I have a session, like I think end of April, to go more into memory. All right. Next week we'll talk about embedding in terms of vector embeddings, which is also part of memory as well. I think this whole memory thing is like the way to go ahead for large language models. And you know, if we have a lot of APIs we want to refer to, we cannot just do in-context prompting of all of them, right? You will exceed memory. So maybe you can only like find out like the relevant APIs to give the description, okay, based on maybe some like similarity matching, or like there could be other ways to do memory. But one thing for sure is there have been some attempts to increase the context length so that, you know, instead of 32,000, we can have maybe 100,000, 200,000. Okay. And I'll just go through in briefly what each of this kind of memory does. So the first is this Memformer that I was looking at. So when I was doing the transformers discussion, I was saying that the encoder for the transformer, this is the encoder. The encoder is something like a memory, because like the decoder does this cross attention to the encoder. The key and the values over here come from the encoder. So it's like referencing a dictionary. And then your query comes from the decoder. So in some sense, your encoder is the memory already. So we can augment the memory using like an external memory here. That will also be done using key value here. So this is done in Memformer, where you augment with an external memory. This is like an RNN memory, where it's a fixed state like of k dimensions. And this memory can then be rewritten at the end of the time step to decide like what to keep, what to forget. All right. Over here, this will then go to this part here. Okay, so this is a quite interesting way to embed memory because it's trying to use the encoder and augment it with external memory so that you can like maybe learn a longer context. Okay? But my key gripe about this method, although quite cool, is that the encoder mechanism is typically not used for GPT. So it'll be a bit more like cumbersome to include it if you want to do it for modern architectures. And the second thing, which is my biggest gripe, is that this memory here is not a dynamic length, this is a fixed length. So, you know, RNNs, they suffer from the memory bottleneck. So transformers, by doing it in parallel, helps to bypass the memory bottleneck. So by going into a fixed length, actually you have a bottleneck as well. So this is one of the early attempts. Okay, I wouldn't say early, it's 2022, but one of the earlier attempts to try to augment memory to transformers. And I would say that this one more or less has difficulties right now in current architecture, mainly because it's trying to do it in the form of an encoder. But I do like the fact that it's trying to augment memory in the form of an encoder. So let's see what like another paper did. And I think this paper has a lot of promise. This paper does it using a key value pair embedding of other neighbors. So basically the layer before the end layer here, every time you pass through the transformer, you take this embedding space, which is like not the earlier embedding space. This embedding space has already been like sort of referenced, like, you know, the causal attention, like each embedding space will already be affected by the earlier embeddings. So these are like the causal embeddings already. You store this key value pairs, all right? And what you do is whenever you have an embedding in the future, apart from just this few embeddings, like these 6 squares that you see over here, you also reference like your earlier part, what you have seen in the document, maybe. Like if you are talking about Fibonacci sequence, maybe there's a definition of Fibonacci sequence in the earlier part of the document. You can actually solve using semantic similarity in the embedding space. You can then find out the k nearest neighbors. So to find out the k nearest neighbors, we have discussed this before, like scan or FICE. These are 2 different methods, but most of these methods, right? In fact, both methods also do this. They use L2 distance. So they just take the like squared terms of the difference in the vector in order to find out like in an embedding space, like is my query here? How close is my query to my key? And then you just take the L2 distance to find out. And then you can do this using approximate methods like this scan or FICE, which can scale to billions, okay, without much increase in complexity. So, you know, theoretically it can go to unlimited, but it comes at the cost of like referencing your key value, right? I have a way to do distributed memory where you like send out like a signal to all your memory nodes, and then your memory nodes will then respond back based on like the similarity. The faster you respond, all right, the more similar you are. So this kind of distributed memory system, I haven't seen anyone do it before, but this is what I was thinking of doing. Okay, because this distributed memory system, okay, scales up without any complexity, because you just need to send it to everyone, and then based on the fastest one that replies you, that's your nearest neighbor. Yeah, but the problem is it doesn't work in current architectures because current architectures are GPUs. They do matrix multiplication. So, you know, you do scan or FICE, you can do matrix multiplication to find your L2 distance pretty fast. Okay, this kind of distributed architecture is like when you have distributed agents, you know, you kind of need to build that kind of architecture, which is not in current GPUs. So yeah, I believe if you can build this kind of distributed memory system, you will have solved the problem of like referencing unlimited memory. You will do it at almost no cost at all. Yeah, the inference time is the same, right? But the main thing, we can talk about this more like at the end of April. I have one session for this. And the key thing I want just trying to highlight here is that with this unlimited context length, you can give it the benefit of all the past memory. So imagine you can give it unlimited context. Like you can tell it, these are the million APIs that you can use. And then you have all this nearest neighbor lookup that your model, at the point of time, when it's trying to find out what it should use, it can look up this table and augment. Okay, it's called memory retrieval, all right? You can actually augment your signals. So what you saw in the JARVIS earlier is that you can actually do in context memory augmentation by retrieval. Okay, this one is basically memory augmentation by embedding space. So it's a bit different, yeah, because all these are the earlier memory. So if we use this kind of architecture, of course, we cannot do this like off the shelf. You need to actually code the transformer out yourself because you need to do this KNN step here. If you can do this, you can theoretically have an unlimited length of context. Okay, I wouldn't delve too much into it because this is not the highlight, but I like this method a lot. There'll be one session dedicated just for this method. And lastly, this is a very, very cool thing that I've seen recently. This is about using GPT as a system of GPT agents. So you have one to create a task. Okay, so your user provides the task. Okay, you have an execution agent. Okay, and a task creation agent. So the task creation agent will like create a task. The execution agent will sort of execute it. Okay, and then you can reference like task result pairs from memory. So it's something very similar to what you see in the HuggingGPT system. You have previous examples to like help the agent create the right tasks. All right. And then after that, you can also have a prioritization agent to sort of prioritize what task to do next. So this is kind of a very interesting system because it uses memory, it uses some sort of hierarchical relation. Of course, this is just one example of what can be done. The key idea is that you need the GPT agents to be an ecosystem. You need some form of memory to ground the context. And with this tool, with some other prompting techniques, I think GPT-4 or further systems can actually be more and more powerful. Okay, so yeah, you all have any questions so far on the memory stuff? Maybe I just take a quick pause here if you all want to ask anything. Okay, if not, in the last 15 minutes, let's just do a discussion. So I think the key point to note is LLMs currently cannot learn. I mean, because you don't have the ability to fine tune yet. Yeah, maybe you will be able to fine tune next time when OpenAI releases the ability to fine tune models. All right. So how can we, if we cannot fine tune the LLMs? In fact, LLMs also learn quite slowly because like if you want to talk about neural network weights, you need to run through many, many epochs. Sometimes you need to overtrain it in order to perform well. There's some techniques for this. Basically, weights update quite slowly. Okay, but memory updates quite fast. So I was thinking that you can actually use some form of memory storage, memory retrieval. This will be very important to learn because by storing the right memory and retrieving them, you are essentially learning. You can store relevant task input and output pairs, and then you can use it to ground the generation, like what we saw in HuggingGPT, right? Can the APIs be learnable? Okay, this is also quite cool because, with what you saw in the TaskMatrix.AI, you can actually tell the API, okay, you failed on this case, you pass on this case, you fail on the other case. So this API, you can actually, if this was done by an LLM or something that can self-learn, you can actually learn from the failure cases and improve it. And the next time the API might be able to succeed. Or maybe you will learn that you shouldn't use this API for this particular use case. So the learning can happen at two levels. It can happen at the meta level to use APIs, or it can happen at the API level. So I think all this have a lot of promise. If we can let the API even be like the memory retrieval API, like the fast and slow, the slow mechanism where you retrieve memory, I think all this have potential to make GPT with memory augmentation or with adaptable API augmentation. All this will let GPT seem to be learning, all right? Because by calling the right APIs and the APIs updated to the environment, so you are sort of learning. Yeah. Anyone got things to add on this point?
Yeah. Hello, can you hear?
Yes, I can hear you.
So actually, I don't know how to think about it because I kind of stereotypically think of API as just some piece of hard-coded software. So you are suggesting to treat API as another learnable model or the agent, is it?
Yes. So the API can be an agent. That is something like it can be another language model. It can be a memory database. Yeah.
But the whole point, I thought the whole point of using API is to ensure the reliability. For example, if we treat Wolfram Alpha as an API, surely you don't want it to be learnable, right? Because the whole point is to be symbolic.
Oh yeah, but if let's say it fails on a certain case, like it fails to define prime numbers well, then you can sort of like add in a case to learn prime numbers well. Yeah, so
No, but that becomes learnable as in you inform the developer to improve it, right? Not the model itself learn, right?
Right now,
I mean the APIs.
Right now you inform the developers because APIs are developed by developers.
Yeah.
But in the future,
okay,
in the future, I can imagine it to be the API will just be a self-learning system.
Okay, so in a nutshell, my concern is if we make the APIs learnable, then I worry the reliability aspect might suffer or might compromise. That's my concern.
Oh, of course. Then you can do like some form of A/B testing, like you learn and then you see whether it works for more use case. And you keep the original model. Then, after you do the change, if it kind of doesn't do well, then, you drop the change. You can do some form of like A/B testing or some mechanisms whereby you can try out different versions of your API and see what's better. I mean, there's a lot of possibilities in this area.
I mean by reliability, I mean the hallucination aspect. Because you got me right. Because if it's the learnable model, it might also subject to hallucination.
Oh, all right. I get what you are talking about. I mean, if let's say it's a LLM, right? Yeah, that might be a concern as well. Yeah, definitely. Yeah. Okay, let's move to the next question. So this is the thing with additional APIs, like you want to scale to millions, you might need to have a lot of tokens to ground the context. So like your in-context learning, which is your prompt engineering, might not be able to handle that amount of tokens. Okay, right now if you can fit into your in-context prompt, it can do a lot of things already. Okay, it can behave the way you want it to be. Very cool, because like you just need to tell it, you are a what? Like you are a memory retrieval tool. Then you can straight away retrieve memories. Yeah, I mean I just did that. I mean later if there's time I can show you what I did with GPT. I use it as a way to retrieve memories, retrieve like state action trajectories. I had a very fun time playing with it. All right. So I think in the future, especially when we have like Socratic models or more like recurrent communication between different models in a larger ecosystem, we will have this problem of not enough context length, especially if you don't want to fine-tune your models. You want to just increase your context length. How do we solve it? Okay, this will be about the memory augmentation techniques within the GPT model itself. So something like what you saw in the memorizing transformers earlier. So I think this is something that needs to be looked into, because I'm very sure the 32,000 token length for GPT-4 will be exceeded quite easily with the way we are using it now. All right. Okay. Any comments on this? Okay, if not, the next one. LLMs are not known to be robust. This is a very big problem because hallucination is a huge thing. How do we ensure that it's able to learn the API call in a few short manner, like in order to like know what are the sub steps to do, what are the APIs to call? So this one actually people have realized that you can solve it by describing the API rather than
the wording is really weird. Okay. Yeah. It's negative. So what you're saying is LLMs are not known not to be robust. What do you mean by that?
Oh, I think there's a typo here. It's not.
It should be not known to be robust, right?
Yep, you're right. So this one, somehow, if you just say that you must exactly output it, when you say exactly, somehow it doesn't hallucinate that much. So maybe we can curb the problem of hallucination by asking it to strictly follow like the guidelines. Yeah, so this is something that is a work in progress, but if you are able to reliably call the APIs, all right, and then these APIs can sort of do the tasks of like more specialized tasks like math that the LLMs are not very good at. This is a very, I think this will be a very strong system. Like LLMs as the interface to call the APIs. As long as they can call them at the right time, right? And the API executes perfectly. This is awesome. Okay. The main thing is like, how do you know which API to call? And this one, right now, we don't really have an answer, because if we cannot train the base LLM, what we can do is we can use like maybe memory retrieval to sort of do few shot learning, which is what HuggingGPT is doing. Okay, but in the future, if let's say you can do some form of fine tuning, and maybe you can actually fine tune with examples. Although I have a suspicion that fine tuning may not perform that well as like few shot prompting, because when you do few shot prompting, you can like give it more descriptions and everything. If you want to train weights, you will need a lot of examples to train the right weights. So I have a feeling that fine tuning may not work as well as your few shot prompting. So when that's the case, then maybe we need to work on this part. We need to work on increasing the few shot prompting context length. Then you can just do your few shot prompting there. Yeah.
But by the way, what do you mean by learn the API call in a few shot manner?
It's able to learn what to call and learn the parameters of what to call, like the inputs to the API. Yeah, because you need the LLMs to also process the data in the right format.
Currently, I assume that it's done via some rule-based, right? Like, for example, because we know the LLMs are just expecting a text input. So if let's say you're receiving image, you just call some API to try to describe the image for the LLMs to parse the data, right?
Yeah, you can actually do it in like what the HuggingGPT is doing. You give it the list of examples like that. This is the few shot prompting. This is the example-based prompting. And then you can also give it like the list of available like things you can do along with the format of like what to input, what are the arguments to go in. Yeah, so this is few shot prompting. So right now it's able to just learn by this kind of few shot prompting. Yeah.
Do they call like multiple image processing APIs, or it's just one, but they don't release it to us?
You can put as many APIs as you want in your available APIs. The only thing that as I was saying, the only thing that is stopping you from putting more here is that your context length will be reached quite easily. You have only 32,000 tokens. So you can only put a limited number of things in your in-context prompting, in your in-context prompt. Yeah, if you want to do more, you probably need to fine-tune the model for like the earlier APIs or increase the context length, which is, I would say that this will be a huge area of research, how to increase the memory, how to increase the context length for large language models.
Maybe not increase, just maybe have it such that you have a pipeline, like it segregate one part to a sub portion of the LLMs, and then you have another LLM working in parallel that's doing the thing, so you can actually partition the context.
Yeah, possible. It just costs more because you need to call the model more and also has some latency. So these are some things to take note. So actually the training of the LLMs or the putting of LLMs into a system is not so much a next token prediction task anymore. I mean, we are beyond that stage now. It's more or less an engineering task to see what is the best structure to fit in. So it's very exciting because you don't even need to train the model from scratch anymore. It's more like, how do you augment the APIs? How do you interface the APIs? A lot of work is being done on this right now. This is a very new field of research.
Sorry, actually, what's the technical challenge here for increasing the context length? I didn't get it that part.
Right now, if you look at the transformer architecture, if you want to increase the context length, you need to do attention on all your front context, which is intractable because like it scales exponentially. Like let's say you have n different things to compare to, your attention mechanism needs to compare to the concatenation of like all these vectors.
Isn't that just n squared? Why is exponential?
N squared? Polynomial, maybe so, polynomial, not exponential. Yeah.
No, I mean the complexity of training transformer is n squared, right? Because for all the token in one sequence, you want to attend to every other sequence.
You want to attend to all other tokens, yes, correct. Sorry, all other earlier tokens. And this
that's
is
n times n, right?
That's
n times n.
Yeah, so the transformer architecture is like this QK transpose, okay, divided by square root d. I mean, the divide, we can take away that. It's actually this softmax of this divided by some constant or square root of dimension. And then after that, you or maybe I just write in text is easier. So the attention mechanism takes this Q, K is like your over square root D. Okay, and then you do the softmax of this times your V. Yeah, so you kind of need to do the attention across all the earlier vectors of your various keys. Yeah, so that will sort of, as you said, this one will be a n squared, where n is the number of tokens. Yeah, so this one right now is 32,000. Maybe in the future when hardware has improved, you can have more context. But if not, you have to find other ways to artificially increase the context length, like maybe using the memorizing transformers. If not, you will have a problem of scaling up, like the context length, because your hardware cannot support. Yeah, does that answer the question, Zayu?
I need to think about it, but thanks for the.
Yeah, I mean, if
As
not,
in,
we'll just
I
have
get why
unlimited
he's
context.
asking that, because he's thinking, from my understanding, he's from computing, right? N square in computing for algorithms is considered okay, is a good standard. But in our case, N square in here, because the context set is a very, very finite resource, so it's still very hard to scale to very large
Yeah, it's like doing a
sequences.
matrix multiplication. How big can your matrix be? How big can your GPU support the matrix multiplication? There are practical considerations to think about. We are restricted by the GPU capability, actually.
Okay, maybe just to add on my 2 cents, I can think of a few ways off my head how to address this problem. One is I saw something along the lines of restricting the focus of attention. So you compromise the amount that you can look back versus emphasizing on the immediate locality. So you can do that with some kind of masking system in the softmax calculation. That's one. Then the other is I saw something about dot product attention being not the only way to as in it is not the only way to do things. You can also do things like pooling, like convolutions and so on. So instead of doing scale dot product attention, you can do something there as well.
Or you can also do distributed attention. Yeah, you can do attention
like the
in
kind of gating mechanism, like GRU's gating mechanism. Yeah. So instead of doing like n square, so now I think with the gating mechanism, then it's significantly lesser than n square.
Yeah, definitely. Yeah, I think this is a worthy area of research actually, because if you can scale up the amount of attention you can do, you can scale up your context length. At least this is my understanding of why we cannot scale it up. It's because of the attention mechanism.
As in, if you partition it itself, you can reduce the n square into n log n. But I guess you're making a point that you need to increase the number of machines in that case.
Maybe, yeah. I think the best way is still to do distributed. Like you just take one node and then you send out to all the other nodes. Then the other nodes will return back the similarity. That will be able to do it like unlimited number of nodes. Yeah. So right now the architecture doesn't support this kind of distributed way of attention. Okay, so let's move on. Maybe just end this in 5 minutes. I got to go already. Next is, should we just do end-to-end training or train the various modalities separately? All right, so this is my opinion. I feel like end-to-end training is perhaps very difficult because, as you know, in deep learning systems, if you make everything end-to-end, you kind of need to train with a lot of examples to learn the right kind of weights for the first model, right kind of weights for the second model, and so on. But if you fix maybe the first model, fix it as like clip embeddings or fix it as some form of embedding space that is already pre-trained, then it'll be easier to learn the subsequent downstream models. So similarly for LLM interfacing with tools, if you want to learn both jointly together, you will need a lot of examples. I think I'm more in support of training the various modalities separately. Then you can just train your API separately, and if your API improves, your entire model can improve. And the LLM interfacing to API, this part can be trained separately as well, using better prompting techniques, few-shot prompting or better memory techniques. Any comments on this? Okay, I think
just one small comment. Okay, never mind. I think no comment other than agreeing with you.
Oh, okay.
No, because I do multimodal learning as well.
Yeah, yeah, definitely. The multimodal part, right? I think it should be done separately for each of the modes, because you train jointly, again, you need a lot of examples. It scales, I like to say it scales exponentially. I don't know whether that's the right word,
I don't think it scales exponentially, but I agree with you that probably you get better performance by training them separately. That's one thing. Another thing is because sometimes you don't have all modalities present. So if let's say you're going to do an end-to-end training, then you have to have all modalities must be present in order to use that model. So it puts a restriction, you know, on the data that you have. So if you train them separately, then you can have different systems depending on how many modalities you actually have at inference time. So
Okay.
that's an advantage of separate training.
All right,
Okay,
thanks.
nothing else from
A way you can cheat people in AI on buying your argument that it scales exponentially, right? Is you think about it in terms of within the feature space, because if let's say from one feature to another feature space, it's like scaling from dimension of D to let's say dimension of D times X, then you can say, oh yeah, it's scaling by dimension of X, so it's scaling exponentially in that case. But I do agree that, you know, most cases we don't want it to train end to end. Because if you do that, like for example, if you want to change your API to another one and you have to decouple the entire model, then doesn't make sense to like import it as such. And usually I observe that if you train it separately, it's more robust. As in, if you train end to end, chances are it's getting a better test or training performance. But if you train it separately, usually you'll get a better robustness to your models.
Yeah, very good, very good. Yeah, I also agree with that. Yeah, so I do think that we shouldn't train everything end to end. We shouldn't train tabula rasa. We should actually have some fixed bias if possible to speed up training and so on. So all this can be incorporated as well. Like fixed bias, it can also be in form of grounding. Like you can give it some context, like you are not supposed to do this, or you are supposed to do exact file names, that kind of stuff. These are like some form of fixed bias. I mean, Transformer has a bias in terms of the tokens having some position embeddings as well. I'm still thinking whether or not we can do better, but right now it seems to work. So, you know, if it works and it can scale, why not? Right. In the future, I also intend to come up with a paper that talks about memory in terms of multimodal memory, where you can reference one memory and link to the rest. So this is something that is quite exciting for me as well, because we are moving to multimodal already. AI has moved so fast. Like 5 years ago, we can't even dream that this was possible. But now I feel like all the tools are right, and it's about how we integrate them together to form the AI that is a learning system. So quite excited to explore this. All right. So the last two questions, let me just answer very briefly. Like memory benefit tool usage, of course. Okay, then the question is how to design this memory. So this one, we'll talk about it at the end of the month. All right. And can multiple GPT systems create an ecosystem that is beyond the sum of the parts, the capabilities? I think yes. I mean, I believe in emergence, and definitely this should be possible, but only time will tell. So yeah. Anything to talk about for the last two parts? I can maybe take one or two questions or one or two points.
1 point. So in the case of two model, one used to run another, right? Like how they are doing it, like some of the company are doing it. I think you also mentioned about it.
It's either hierarchical or recurrent, or it can be
Yes.
both together, hierarchical and
But
recurrent.
my concern is as long as the grounding mechanism is coming from a language model as well, there is always probability of jailbreaking, because you can indirectly jailbreak the grounding model. Although I mean, granted it's harder, but there's still a possibility. Yeah, that's my comment.
Yeah, I mean, you can put the jailbreak part as a higher level model so that you cannot bypass it with user instructions.
No, as long as there's communication, you can take advantage of the communication. Indirectly jailbreak it. I mean, at least conceptually, I think that's possible.
Yeah, then you have to put some safeguards. You don't let the top model be affected by the bottom.
But as long as it's a language model, it's prone to prompting, right?
Okay, yeah. I mean, fair point. I don't know whether you can prompt and affect the meta model. That's something to think about. Yeah.
Yeah. It's just my current thought. I also think more on that.
All right. Thanks, Larry. Anyone want to talk about the final comment? Okay, if not, I would like to end here. I think this whole LLM with tools thing is very interesting. And if done properly, this will be the next wave of AI. In fact, it's already the current wave of AI. And the next wave of AI would probably come when we can incorporate better memory systems to learn from examples, to learn more adaptively, and also to be able to learn and train the APIs, learn to train the interfacing with the APIs. This adaptable system, if it can be done well, right, will definitely be very powerful. And you can see this powering a lot of your applications already. So LLMs with tools, the idea just came out like a few months back, but you can already see a lot of applications being built on it. And I'm very excited to see what can be done. Very excited to see how we can interface the memory as well. And yeah, we'll talk more about memory embeddings next week. And yeah, thanks for coming. See you all next week. Bye-bye.
Thanks, Xiaoming. Thanks, everyone. Bye-bye.
Bye.